Okay, so now we have covered the charge transport in organic semiconductors, and what remains is optical properties of these materials. Very briefly, I have been introducing the idea that the band gap determines the optical and electrical properties. We've already seen how the change in band gap due to different things, either due to tuning of the backbone, the polymer backbone, the side chains, by playing around with molecular weights of polymers. And essentially the packing can all change the backbone. Well, sorry, it can change the band gap a little bit, and that has an effect on the electronic properties. So now we're going to focus on the optical properties, which includes both absorption and emission. So now you know you're completely familiar what conjugated polymers are, right? They are alternating double bond, single bond chains of chromophores. And the molecular structure itself is not sufficient to really describe the optical properties, but obviously one needs to know the molecular structure, and also from that also get an idea about the band gap, know the band gap, and then we can have a better idea about what the optical properties are. When we excite a conjugated polymer, we're generally talking about singlet states. So in a couple of slides, I'll explain exactly what I mean by singlet states and what else there is as opposed to singlet states. And we generally excite the polymer with light. Light is an electromagnetic wave. It has both electric component and magnetic component. The magnetic component is about 5 orders of magnitude at least smaller, so we tend to usually ignore that. But from the electronic component, we end up having a transition dipole component, which tells us whether a transition is allowed or whether it's strongly allowed, weakly allowed, or so on. This we call either the oscillator strength or the transition dipole moment. And in general, this process increases with the number of pi electrons that we have. So basically how we define the conjugation length. Conjugated polymers in general, they have strong absorption coefficients. So you can see when we're talking solutions, we call it, we label it with epsilon. And this is called the extinction coefficient. And in films, we tend to try to classify it or quantify it or label it just with alpha. But this number 10 to the power of 5 is generally rather high. And so this is all absorption. And then when we come to emission, they have a relatively efficient and fast emission. So if we excite a system, a polymer, typically it will live about a nanosecond in its excited state before it then relaxes down to the ground state. And these are the 100% or 60% is the quantum yield. So basically how much radiation is coming out when it's emitted. So we'll go into details as we go along. Okay, so now, yeah, we already know this. The optical properties can be described in molecular picture. And okay, so let's get started about describing the optical properties. So whenever we want to talk about excitation, we refer to Jablonski's diagram. Okay, yes, yeah. So you're in your ground state, your molecules, all of your HOMO is occupied here. So All the spins are paired, everything is in the HOMO state. And then we introduce a light source which has a certain energy. As long as the energy is exactly equal to the difference between S1 and S0, then we call this a resonant state. So a resonant excitation. So we don't have any loss in terms of exciting these two higher states if we only want to go to the very lowest state of the S1. So we excite the system from the HOMO to now one electron is in the LUMO, and we have created the excited state. As you can see, you have these very thick solid lines which defines the electronic states. S0 ground state, S1 first excited state, S2 second excited state. The S stands for singlet. And as we have said before, in the singlet state or in the ground state, we are always, the spins are always paired. So one up, one down. Now you have these finer lines in between each of these excited states. These are the vibrational states. And each excited state or electronic state has its own vibrational states. Now, the energy that is required to excite an atom or molecule or polymer or whatever we're exciting electronically is always greater than the energy that we need to excite it vibranically. So you can see going from S0 to S1, the electronic excitation, it requires more energy than going from this vibration level to this one, or from this one to this one. So these lines are called the vibrational levels, and the solid lines between S0, S1, or S2, or whatever, Sn, is called the electronic excitations or transitions. If we actually did a high resolution, so typically in gas phase you spectrum, then we do not actually just see one single peak for each electronic transition, but you can actually also see the fine structure which corresponds to the transition between the different vibrational levels. And when we have the simultaneous electronic and or vibrational transitions, then this is known as the vibronic transitions. So in this case, when we excited the system, one arrow just goes from the electronic state S0 to S1. The other one still goes from S0 to S1, but instead of going to the lowest vibrational level, the second arrow here is going to the first vibronic level of S1 state. Then the arrow after that shows that an energy which can take the electron to the second vibronic level of S1 state. And the one next to that is taking it to the third vibronic level of S1 state. So each of these lines, it starts with 0, and then it goes up, the vibronic levels. Okay, so now we are in the S1 state. What happens is, if relaxation wants to happen back to the ground state, if we are in the higher vibrational levels, then we need to have vibronic relaxations of those higher vibronic levels to the lowest vibronic state, until we reach the lowest vibronic state of the S1 electronic excited state. So the relaxation from the vibrational levels to the lowest vibration level is called vibronic relaxation. And then once we are on the new node, so the vibronic level, the 0 vibronic level of S1, then we have the option for the emission. Emission is a radiative process. So if we go from the lowest vibronic level of S1 to the lowest vibronic level of S0, you have this arrow here. You have fluorescence. Fluorescence is the process when you are actually radiating an emission out. If you go from, if you do the full electronic transitions before going to the other vibronic levels, then this has the highest radiation coming out of the system. If we, however, don't go to the lowest vibronic level of S0, but rather we end up at S1 or S2 or S3, then as the vibronic level is higher or is further away from the lowest vibronic level, i.e. nu naught, which would be here, then our radiation yield will be lower. And then the rest of it has to be accompanied by vibronic relaxation again. So imagine we are on S1, we are on the lowest vibronic state, and we have the radiation, we have the radiative emission until S0 nu 1. So it's this arrow here. Then the remainder of the vibronic level will relax vibronically. And this is non-radiative. So these ones we cannot see by eye, for instance. However, when we have fluorescence or radiative emission, then we can see it in theory with eye. One thing to note, so let's go back to the absorption, light absorption. When we are here, when we're exciting the molecule, we have to make use of the Born-Oppenheimer approximation. What does it tell us? It tells us, or it states that the motions of electrons are usually much more rapid than the nuclear motion. What are the nuclear motions? They are those that are occurring during vibration. What is the basis? Where does this approximation come from? It comes from the fact that the nuclei is orders of magnitude heavier than the electrons. So what is the mass of an electron? Is something 10 to the power of minus 31. What is that of the nuclei? Is 10 to the minus 27. So you can see it's orders of magnitude different, which means that when an electron moves, essentially the nuclei is almost stationary. So any changes in the position of the nuclei is either neglected because it takes so long for it to be to occur, or it immediately is accommodated by electrons which instantaneously shift position to adopt the most energetically favorable arrangements. This will come into play when we talk about the shift between absorption and emission. The other implication it has is that, or implication in terms of a positive thing, the total wave function is the product of separate independent contributions from the nuclear and the electronic wave functions. So in this way, when we want to make life simple for ourselves, then we can treat the wave function for the nuclear separately and that of the electronics and the electronic movement separately. So we won't go into the maths of it, but the one thing you need to appreciate is that the implication of all of that is that the nuclear geometry remains unchanged during the time taken for an electronic transition to happen. And even though we just said this is the Born-Oppenheimer approximation, but this is actually also summarizing the classical statement of the Frank-Condon principle. So we'll talk about this a little bit later on. Okay, so if we don't have fluorescence, The alternative we can have in some systems, not every system, is intersystem crossing, ISC. ISC happens always horizontally, and what that means is that after you have spin orbit coupling, after you have your electron, somehow, instead of it being paired, now it becomes parallel in the excited state. Then the energy of a triplet state, the vibronic level energy of a triplet state, has to be the same as a vibronic energy of your singlet state. So you can see these two energies are degenerate. So they're the same. And this is the only way you will get intersystem crossing. You will not be able to get intersystem crossing from your lowest vibronic level of S1 as from here to the lowest vibronic level of T1. It has to occur between two vibrational levels that have the same energy. So intersystem crossing has to be horizontal, which means that the two vibrational levels between singlet and triplet states have to be the same. And only in that case, then we go to the triplet exciton. Once we are in that vibronic level of T1 or higher T's, and then we need to have vibrational relaxations to the lowest vibronic level of the T1 state. From there, we have phosphorescence. Again, this is an emission of the triplet state back to the ground state. When we go from S1 to S0, we call it fluorescence. When we go from T1 to S0, we call it phosphorescence. And just like fluorescence, either all of it can be phosphorescence radiated, or some of it you may have the vibronic relaxations. Okay, so let's go back to the very first thing, absorption. Generally, we treat our ground state or excited state with these potentials. So we call them surface potential energies or just potential energies, depending whether we're talking about one molecule, one atom, or when we have a polymer. To make excitation occur, the excitation has to always be a vertical transition. So as you can see from these lines, all of the lines have to be vertical. They can't be at an angle. This is also part of the Franck-Condon principle. The other thing that is stated by the FC principle is that during the most intense electronic transition, the molecule remains in the nuclear equilibrium geometry. So you can see, yeah, the geometry of the nucleus doesn't change in the ground state, and the vertical transition is to a potential energy. So now from S0 to S1, this is your potential energy. Where the peak of your wave function here will have the most intense or the most probable transition when it reaches a wave function at its peak. This is because this is a statistically most likely geometry for the molecule. So let's go through that again. So you have to assume that the absorbing molecule is in the ground vibrational level, and it has to always be in the lower electronics and vibronic level, because at room temperature, we don't have enough energy to have an appreciable population in the excited vibrational levels. So everything is always in the lowest vibronic level. Now, the FCP, the Frank-Condon principle, requires that the transition occurs to the vibrational level in the excited electronic state, with the wave function that is most closely resembles the wave function of the ground vibrational level. So given that we always, okay, let me just explain this a little bit more. Okay, yeah, let's go with this one. So this is your potential. These are your vibrational levels. Each vibronic level has its own wave function. So you can see this is a wave function, this is a wave function for nu1, and so on. To get the most probable transition, all the transitions will be vertical. So you go from here to somewhere here. So then the FCP tells us that the wave function of the excited state where we end up at has to be one that most closely resembles the one that we started. So one that looks like this. And what that means is that when you're starting from here, right in the center, you also want to go to a wave function where you essentially have just the wave, that part of the wave function just shifted upwards. So no horizontal shift, but just upwards. And also the fact that the wave function is in the same direction. So here it's facing up, for instance, it's going this way with the amplitude here, whilst this is the opposite. So this ends up being the most probable transition. So you want to have the largest amplitude peak at the center of the wave function in order for your most likely transition to occur. And then, depending on which vibrational level we go to, we end up with an absorption spectrum. Again, this has to be in gas phase where we can actually see all the vibronic transitions very clearly. So if you already said, okay, I'll go into another figure before going into the details of which ones are the most probable and how the intensity will change. So the message is that the shape of the absorption and emission spectra depends on the potential energy curves in the ground state and in the excited state. So both A, what the gap is, how much of a shift we have between the central position of S0 and S1, which will then determine the intensity of the peaks. The determination of the intensity of the peaks is the quantum consideration of the Frank-Condon principle, which all relies on calculating the transition dipole moment, but the calculations and all is not part of your syllabus, so we won't go into it. Okay, so we already talked about this. You have your energy here on the y-axis, you have your nuclear coordinates here, You have your ground state potential, your excited state potential. Sometimes there is no shift here. So the minima of your ground state potential will be in the same place as the minima of your excited state, which just means that your excited state is an upward shift of the potential of your ground state. But this is not the usual case. Generally, we end up having a shift as well in the nuclear coordinates. So we have a vertical transition, but we also have a horizontal transition as well. So yeah, clearly when we have the shift, we say the nuclei has moved. As I have already said, the each vibronic level is labeled as well. And you have these quantum numbers for each vibration levels in each different electronic state. And the wave function for each vibronic level is essentially the probability, well, you have to square it and then take the modulus, but it's probability to find the nuclei at a given coordinate. That's what it means when we talk about wave functions. So we said absorption starts from the lowest vibrational level in the ground state, so nu 0. And the strongest absorption is of S1, from S0 to S1, is to a vibrational level with high probability of initial state nuclear coordinates, which means that you want to have the highest amplitude of your wave function, and the wave function has to resemble, in the excited state, it has to resemble that of the starting point, so in your ground state. So as I said, you need to have a vertical transition, not something at an angle. So this green line is not allowed. Even though you might say, oh, but this is like, this is the wave function that resembles the starting wave function, and we will have the highest amplitude, but because it's not a vertical transition, it's not allowed. Okay. So when we excite, we go from nu 0 to potentially different vibronic levels in the excited state. And depending on where we land, we get a new feature on the absorption spectrum. So let's look at this, here. If we always start from nu 0, and one transition is, which requires the least energy, is from 0 to 0 state. If we're plotting the absorption as a function of wavelength, then this will be the more red shifted peak. Another transition would be from 0 to 1 vibronic level. Then that would be the next one. The next one from 0 to 2 would be the peak after that. And the last peak with the lowest wavelength in place, or the highest energy corresponding to the highest energy, would be the one from 0 vibronic level to the highest vibronic level in the S1. So in this example, it would be 3. And as we have explained already, your 0 to 0 transition is not always the strongest. It would only be strongest transition, i.e. the intensity of the peak would be the highest, if we had no shift in the excited state potential compared to the ground state, because then you would get the highest amplitude. But since it's not the highest amplitude, then it will not give us the highest intensity in the absorption. Okay, so now you know how absorption proceeds. Let's look at this case as well before we just talk about line shapes. Here you have your excited state just shifted above the ground state. And in this case, your highest probable transition would be from nu0 to nu0. And for that reason, then if you look at the absorption spectrum, then the 0 to 0 transition gives you the highest intensity peak, whilst any of the other higher ironically excited states will give you lower excitation peaks. Now, line shapes. As I said, if you do high resolution gas phase spectroscopy, then we can see different line shapes. But before we get into all of that, you have to understand how electromagnetic field interacts with matter, because that's what light is, right? In electromagnetic field. So when an atom or molecule absorbs a photon, all of the energy of the photon has to be absorbed, right? No more or no less. So if it's less than the band gap, nothing happens. If it's more than the band gap, then we have all of these vibrational levels. So if we have the exact energy between E1 and E0 from the Byronic level, then you call this the resonance condition. But this is not always the case. And essentially, it does not mean that the absorption spectrum must be a series of infinitely narrow peaks, because we always have broadening of the absorption and also the emission if we're talking about emission as well, for different reasons. The most fundamental cause of the broadening is the Heisenberg's uncertainty principle. I'm assuming most of you are actually familiar with the Heisenberg uncertainty principle in the context of position and momentum. But as some of you may know, there's also the energy time uncertainty. So just in short, to either recap for those who know or for those that they don't know, all you need to know, you don't need to know too much detail, the uncertainty in the energy and time is related by delta E multiplied by delta T has to be equal or larger than h bar, so the constant Planck's constant h. So a stationary quantum state has an arbitrary exact energy. We know what it is. But the quantum state with a finite lifetime necessarily has an imprecise energy. Therefore, a transition between two quantum states does not always require precisely the same energy. What this means, it means that you get a blurring. So instead of having very well-defined lines, you get the blurring of the energies of the quantum states, and therefore the energies of transitions. Then they change the picture of the full energy of the photons after they have absorbed the energy. So the thing to remember is, so instead of we always simplify things when we're drawing these diagrams over here, right? Instead of having a transition from the ground state to the excited state, a carrying or being brought about by the absorption of photon of only a single precise frequency, this transition is actually being affected by absorption of photons over a small range of frequencies. Don't get this confused. It does not change the fact that each of these photons loses all of its energy when absorbed. It just simply means or reflects the uncertainty in the energy levels of the two states. And so sometimes we get the broadening, which is something called natural line broadening. Okay, so here are some examples of conjugated polymers. And a lot of conjugated polymers have an aromatic unit connected by single bonds. What that means is that, for instance, when they're in the ground state, there might be a strong torsion between the top two aromatic units, which is connected by the single bond. And when it gets in the excited state, it might become planarized. Then, depending on how we're making the solution, well, to begin with, yeah, the solvent that is used, then it plays a very big role in how the absorption spectrum looks like. In general, the absorption spectrum will be very, very broad. And we typically have different effects, such as solvatochromism or ferrochromism occurring in the absorption. So this is a slide which you have seen before. It's P3HT, and as we briefly talked about it, this is the absorption in chloroform, so in solution, which corresponds to this picture here, and this is the absorption of the same thing when spun coated on a glass. So this is the solid state, and this is the solution. So solvatochromism is a process or phenomena that we usually observe when the color, well, you can see obviously the color is changing, the peak in the absorption is changing. The color is changed due to the solute basically being in different environments. So either due to when it's dissolved in different solvents, or when it goes from this state, which is not aggregated, to this state, which is aggregated. And in PPH is very strong. We also saw in the PNDI polymer, where the absorption was changing a lot through different solvents, good or bad, the effect is also persistent. So in systems where the solvent basically plays a key role from taking the system from a amorphous solution into an aggregated one, will change the absorption and the color of the material of the polymer. Now, as you can guess from ferrochromism, what the process might be. In here, the phenomena is based on change in absorption and color due to changes in temperature. So liquid crystal materials are actually good systems to study because they possess different phases based on different temperature treatment. And by changing the temperature, it might be actually small changes in temperature, it might be very large, but generally the transition we get, the 0-0 transition, may change substantially or a little bit in different systems. So here you have this liquid crystalline system where if you heat it up to form the isotropic to its isotropic phase, then the absorption is this red line. But if it's in the liquid crystal phase, then you actually get this absorption, where essentially you've lost this 0-0. Well, you haven't lost it. The intensity is a lot lower of the 0-0 transition, and also there's a bit of a shift where it occurs. Okay, so next we will cover fluorescence and phosphorus. Here is just the overview of exactly of everything that can happen. Okay, so we have talked about vertical transition in absorption, vibrational relaxation, vertical transitions of fluorescence, and vertical transitions of phosphorescence we will talk about now. So let's say we have excited the molecule to S1 level. Now, as we said before, we can either get fluorescence from S1 to S0, or before I talk about this, we can get ISC, internal system crossing, where the spin flips to become parallel and go into a triplet state. Again, I emphasize this is a horizontal transition, so we need to have two vibronic energy levels that have the same energy. And then if in the T1s, if you're in the triplet exciton state now, and the energy is not the vibronic level that we have crossed into, is not the lowest vibronic level, then we will do vibrational relaxation to go to the lowest vibronic level of T1 state. From there, we can have phosphorescence, just like fluorescence, with some differences. The other phenomena that we haven't talked about yet, and we may have, it's when we do fluorescence or relaxation from the excited state to the ground state, is internal conversion. There's a little difference between internal conversion and vibrational relaxation. Internal conversions occur between different electronic states. Vibrational relaxation always occurs in the same electronic state. So if you have a non-radiative process, sorry, internal conversion is also non-radiative. So if you have a non-radiative process from vibronic level of 1, 2, 3, S1 nu free to S0 nu 2, this is combination of vibronic relaxation and internal conversion. Okay, so fluorescence is radiative, phosphorescence itself is radiative, and then internal ISC is non-radiative, IC, internal conversion, or VR, they are all non-radiative processes. When we have formed a triplet exciton, we can always do the reverse of what we did to form the triplet exciton. So we can do the reverse ISC and form a singlet exciton. Of course, it's very important to have the energies of both the vibronic levels and the electronic levels all aligned. Okay, so now we can talk about emission spectrum. Okay, so just like absorption, emission's line shape is also determined from the excited and the ground state potential energies, and it's essentially the reverse. So, in order for emission to happen, we always have to start the emission from the lowest vibronic level of the first excited state. From nu 0, S1, we can then reach different vibronic levels of the S0 electronic state. And depending on which vibronic levels we reach, then we essentially generate the emission spectrum, the line shapes of the emission spectrum. So as it says, in an ideal case, the emission spectrum mirrors the absorption spectrum in the sense that there's no Stokes shift, there's no shift between the 0-0 transition in the absorption and emission, and all the relative intensities of the peaks are the same in emission and in absorption. So just as we had in the absorption, when you have the 0-0 transition, you get the lowest energy peak, it would be here. And this is in wavelength, that's why the lowest energy peak is here. In the emission, the highest energy would correspond to the 0-0 emission, 0-0 transition, sorry. And then the next one would be 0-1, 0-2, and 0-3, so on. So when we have these transitions, we call them fluorescence. Fluorescence is radiative, and in organic or in polymer, conjugated polymers, the lifetime of the fluorescence can vary between 10 to the 7 to, sorry, 10 to the minus 7 to 10 to the minus 10 seconds. So anything from hundreds of nanoseconds to 100 picosecond. But more commonly, actually, it's about a nanosecond. In addition, we said we can also have internal conversion. Internal conversion is non-radiative, and this has an exponential dependence on the energy levels that it's going to. The vibrational relaxation is non-radiative as well, and the rate for vibrational relaxation is about 10 to the 11 to 10 to the 13 per second, which means that this is one of the fastest transitions that's possible to happen. So we always end up having vibrational transitions from the higher vibronic levels to the lowest vibronic level of the excited state. And in fact, it's for this reason, just because this transition, this relaxation is the fastest, then we always start the emission from the lowest vibronic level of S1, and it then fluoresces or phosphoresces or does whatever it needs to do. So always remember, vibration relaxation competes with luminescence, i.e. phosphorescence or phosphorescence or fluorescence. And as I said, we always end up getting the luminescence from S1, so nu 0 S1 to the back to the ground state. So now when do we get internal conversion? Internal conversion happens when the absorption has excited your system to not just S1, but let's say to S2. Emission will always happen from S1. And so in order to reach S1, as we said, vibronic relaxation has to happen in the same electronic state. So first we need to go from S2 to S1. And this is how we have, and this is when internal conversion occurs. The rate of internal conversion depends exponentially on the difference in energy between the upper and lower electronic states involved. So from between S2 and S1. Yeah. And then once we reach S1, if we're in the high vibronic levels, then you have the vibrational relaxation. And then only once you reach the lowest vibronic level of S1, then you get emission. Typically, the energy difference between S2 to S1, for instance, it's smaller than the difference between S1 and S0. So internal conversion is very fast coming for between S2 to S1, but not between S1 and S0. That's why internal conversion only proceeds in higher excited states, but not for the final transition from S1 to S0. Okay. So now we have covered how absorption and emission proceed. Also, just to let you know, when we say we have the emission from the lowest vibronic level, i.e. the faster transitions, it being internal conversion of the different electronic states, accompanied also with vibrational relaxation to allow emission to only proceed from S0, from nu naught of S1, is all defined under Cashel's rule. So this is what Cashel basically said, that the emission always happens from the lowest vibronic level of S1 to S0. So to summarize, all the peaks in the absorption spectrum always originate from nu naught of S0, and so the energy separation between the absorption and emission just between each absorption in the absorption spectrum just indicates the vibrational structure in S1. In emission spectrum, all the emission originates from nu naught of S1, which we just said is due to Cashel's rule, and so the energy separation between the peaks in the emission spectrum indicates the vibrational structure of S0. If you have large rigid molecules, they will tend to have similar geometries in the ground and the first excited state. And as a result of having similar geometries, they will have similar vibrational structure, and the separation of the peaks in the absorption spectrum will be similar to the separation of the peaks in the emission spectrum. This you don't really need to know, but just so you have some sort of appreciation, the intensities of the peaks in the absorption and emission are all related to the quantum consideration of the Frank-Condon factors and principle. And because the geometries, and one can say the vibration structures of two surfaces, i.e. the ground state and the excited state, are similar, one can conclude that a transition from 0 to A could be 1, 2, 3, whatever, in the absorption spectrum will have a similar intensity to the emission spectrum of that same transition. So from A back to the ground state. And now here's a question. As we said, this is the ideal case. The absorption emission spectrum here you have is an ideal case. If I show you this case, right, instead of this, so this is not pentacene. Oh, what was it called when you have 4? I forgot. Anyway, you have this case here, which is the ideal case and mirror image, and you have a more realistic case here of DPH. So why does why does the 0-0 transition not occur at the same energy here in the absorption as in the emission? This is because of Stokes shifts. And Stokes shift results due to redistribution of the solvent cage. I'm saying solvent cage in vertical compass. And what this means is just to better accommodate. So this redistribution is basically there to better reaccommodate the electron density of each state. The arrangement or the rearrangement, so you have the rearrangement in both cases. And in this in this system, in the DPH system, the rearrangement takes place more slowly than either the vertical transition for absorption or emission. And so it results in the shift of the line spectrum. And this is what Stokes shift is. It's just basically redistribution of the Stokes cage, of the solvent cage, sorry. In all of these, there is just, I don't have the example here. There's one exception. So we always said that the emission happens from S1 state, except the case of azulene. In the azulene, Cash's rule is not obeyed. So as I was saying, internal conversion happens in the higher S1 states, so between S2 to S1 or S3 to S2 and S1, because the gap between S2 to S1 is smaller than the gap between S1 and S0. But in the case of azulene, the energy difference between S2 to S1 is actually much larger than S1 to S0. As a result, internal conversion is very rapid from S1, and so S1 to S0 fluorescence is very weak. But instead, the internal conversion from S2 to S1 is very slow, and so one populates the S2 state sufficiently for long-lived carriers to allow fluorescence to happen. And in this case, for azulene, the fluorescence is actually a mirror image of the absorption. So your strongest transition is the 0 to 1 case of the S2 scenario, and you don't have a Stokes shift because your 0-0 transitions are occurring in the same energy, and then your emission, your highest intensity comes from the S2 to S0 transition. Okay. So in this example that we illustrated here, you have the difference between the two molecular structure basically can be summarized as whether you have a linear conjugated backbone or whether you have a more complicated, so it's not linear, you have this two-dimensional conjugated backbone. When you have a rigid backbone structure, then you get a very strong transition in the 0-0 transition, in both in absorption and emission peak. And that's because your nuclear motion is very, very small, or essentially none. So the maximum amplitude or the strongest dipole transition dipole is from the vibronic level of the 0 in the S0 state to the lowest vibronic level in S1 state, which means the 0-0 transition. And pretty much for the same reason, you don't have Stokes shift either. So you end up getting a mirror image of the absorption and emission. In this case, in the DPH case, where you have a linear conjugated backbone, you have essentially change in the bond length alternation, because you have single double bonds. So if you remember when we were doing the calculations in the first slide, actually, in the first lecture, when we're doing the calculations for the potential well, we said that the potential well does actually have a flat edge because we have the alternation between single and double bonds. And the change in bond length results in variation in instability. And so then we also have a shift in when we go in the nuclear coordinate, when we go in the excited state. So the 0-0 transition is no longer the most intense or the most probable or the most allowed transition, rather the 0-1 transition is. And so you can see the highest intensity peak here comes from the 0-1 intensity, both in absorption and in emission. And because we also have the shift in the nuclear coordinate, it means we will have rearrangement as we excite the system for the solvent cage. So we get this shift in between the emission and absorption. So this is the ladder type polymer, which is called PP or PPE. And in this case, we have a rigid polymer backbone again. So same as this 2D conjugated case. So now we have a small molecular geometry in the ground or the excited state. And so the 0-0 transition is the most probable one because it has the highest amplitude. And we don't see any Stokes shift either. Okay, so here is when we have a very rigid molecular structures, and what happens as we go from room temperature to low to reduced temperatures. As it can be seen, the vibronic levels, as we reduce the temperature in all cases, the vibronic levels become more pronounced compared to room temperature. And whilst in case B, where the rigidity is less than case A, we seem to appear to have a Stokes shift. When you lower the temperature, then you can actually see the vibronic level very strongly, and you can see you have no Stokes shift. So, in cases of non-planar conjugated polymers, the absorption is very broad, and it's the broadness is due to the distribution of twist in the conjugation and the conjugation length. So if we remember, actually we gave one example before, that in the ground state, there's high torsion between two aromatic units because we have a single bond. And that causes a lot of the twisting. So when we go from the ground state to the excited state, there's actually a big Stokes shift, or there's a large coordinate shift, which also results in a Stokes shift, but also it also means that the absorption itself is very broad and featureless, so you cannot see the vibronic levels here. And then when we do the emission is from the longest and the most planar conjugated unit. It ends up having more structure, but you also see that now we don't have a mirror image at room temperature. We don't have a mirror image between absorption and emission, and we also have a Stokes shift between them. Okay, so that's all fluorescence, all the knowledge you need to know about fluorescence. For phosphorescence, for fluorescence, one thing that I always said is that you don't change your spin. So you're always in the single state, right? In phosphorescence, the first thing that needs to happen is that we need to have a change of spin. In order for the spin to change, we need to have spin-orbit coupling, and usually spin-orbit coupling occurs best or the most efficiently when we have heavy elements involved. That's not to say when we have typical organic polymers, we don't have any spin-orbit coupling. We still get some spin-orbit coupling, but it may just not be as efficient. So for spin-orbit coupling to occur, the only thing that needs to change is essentially the spin of the electron in the excited state. Once the spin flips, we now go to the same isoenergetic vibrational level in the T1 state, and from there we need to have vibrational relaxation to the lowest vibrational level of T1 state. From there, we can potentially have phosphorescence. Phosphorescence is very long-lived compared to fluorescence. So fluorescence was nanosecond source of lifetime. Phosphorescence is about, it could potentially even be microseconds or milliseconds. And the reason for that is because going from T1 state directly to S0 state is not allowed. The spin needs to be flipped again, so it's paired in the ground state. Because of that, it will take a very long time for the electrons to flip its spin and reach the ground state. And so the lifetime is essentially very long. There are cases where we would like to have the spin long-lived, sorry, the lifetime long-lived. So we want to be able to do this flipping of spin. And for those reasons, we end up using these heavy elements. Let me just go back. Heavy elements in order to induce spin-orbit coupling. So one thing I am a little bit vague on is this phosphorescence. Phosphorescence itself is radiative, but because we need to have the spin-orbit coupling to flip the spins back to being paired in the ground state, we may also have other ways of losing the excitation on the triplet state and then have radiation. One way of doing this is basically if you have two T1 states, you want to annihilate them to form a S1 state. This itself will be non-radiative, but then when you're in the S1 state, then you can decay radiatively as fluorescence. So it gets a bit more complicated, but the very basic knowledge that you need to have is that phosphorescence itself is non-radiative. Sorry, it's radiative. Okay, to put emission into context and make it more meaningful, we have to relate it to quantum yield. So basically, when we say something is radiative, we want to know to what percentage its radiation it is. And that is the quantity that is used to define the efficiency of radiativeness, or even non-radiative part, is the quantum yield. So we can talk about photoluminescence quantum yield, which will talk about how radiative the transition from S1 to S0 is. So the quantum yield measures the efficiency of a process. Now we can have quantum yield for emission, for absorption, for non-radiative emission, and so on. So the overall quantum yield, the overall quantum yield for a, say, reaction of excitation. So we have molecule R, we shine light on it with energy h nu. We excite the system into S1, so our molecule is excited, and then it decays down to the ground state. So the overall quantum yield for this reaction would be the number of reactant molecule which is consumed divided by the number of photons absorbed by R. So it's essentially in this case, when we're actually looking at absorption versus emission, is how much emission we had compared to how much photon was absorbed by the molecule. So in general, you can say that the quantum yield is usually the number of the product molecule, whatever the end result is, divided by the number of the photons or molecules in the beginning, in the initial state. And it's always this ratio of output compared to the input that defines your quantum yield. So if we're talking about quantum yield of phosphorescence, then it's the number of photons emitted via phosphorescence itself divided by the number of photons absorbed. This gets very tricky because you have to bring in inter-system crossing as well. So because when you absorb the photon, we don't get a transition from singlet state of the ground state to T1. This transition is not allowed. Instead, we have to go from S0 to S1, and from S1, then we have inter-system crossing, so we have to calculate this as well. And then we have phosphorescence. For fluorescence, this would be a lot easier because then it's just the number of photons emitted via fluorescence divided by the number of absorbed photons. So if we go back to the phosphorescence case, the actual quantum yield would be the number of, well, your denominator will be simple. So that would be the number of photons, absorbed. On your numerator, you should consider the number of excited molecules that may fluoresce back to S0. Then the internal conversion, so the number of molecules that may internally convert back to S0. Then you have the number of excited molecules that can phosphor back to S0. And you also have to include the inter-system crossing. So the number of molecules that did the inter-system crossing. So calculating phosphorescence quantum yield is a lot more difficult. But you have to bear in mind that the quantum yield of everything, the sum of it has to equal 1. Not greater than 1, not less than 1. Okay, I think we will end this lecture here. And then afterwards, we will carry on with energy, with lifetime energy transfer, also this oscillator strength that I have mentioned a couple of times now.